Alright, so today we're going to talk about section 410 and 411. That is right triangle trigonometry and its applications. Alright, so we've seen the definition for the trigonometric functions for a right triangle, so let's just recall the trig ratios. Let's say we have this right triangle right here and some acute angle theta. So we have defined the sides previously in this fashion. So we know that this is our hypotenuse. Here we have our opposite side. That is because it's across from the angle, it's opposite the angle. And here we call this the adjacent side, right? So we define the six trigonometric functions in the following way. We know that the sine of theta is equal to opposite over hypotenuse. Cosine of theta is equal to adjacent over hypotenuse. And the tangent of theta was opposite over adjacent. Remember, we had a quick mnemonic to remember these. It's called SOHCAHTOA. SOHCAHTOA. This will help us to remember these ratios, right? So sine is equal to opposite over hypotenuse. Cosine of the angle is adjacent over hypotenuse. And tangent's opposite over adjacent. Now the other three trig functions we can get simply by just flip-flopping the fractions on this side. So remember, sine of theta corresponds to cosecant of theta. It's the reciprocal, which would be hypotenuse over opposite. The secant is the reciprocal of the cosine, so that would be hypotenuse over adjacent. And the cotangent, the reciprocal of tangent, is adjacent over opposite. Okay. So with these ratios, we can start finding lengths of the sides of a right triangle. Okay. So let's do an example. We want to find the exact value of the six trigonometric functions for the following right triangle. So say we have this right triangle here. Our angle theta, let's say, is right there. And we know these two sides, 8 and 15. Okay. So what we want to do is just find the sine, cos, tan, cosecant, secant, and cotangent ratios for this particular triangle. Now before we start, since we only know the adjacent and the opposite sides, let's go ahead and first start by finding the hypotenuse. So remember that the hypotenuse can be found by using the Pythagorean Theorem. So we know that c squared is equal to a squared plus b squared. Okay. So recall that c is the length of the hypotenuse, and a and b are the lengths of these legs of the right triangle. So here we're trying to find c. So we know that c squared would be equal to 8 squared plus 15 squared. And you can go ahead and find that using a calculator. So with these trig, the next couple of sections we will be able to use our calculator to find these values. 8 squared plus 15 squared is 289. And the square root of that is 17. So again, to cancel this square, we need to square root both sides of the equation. So C is 17, therefore our hypotenuse is 17. Now we can start to form the trigonometric ratios. Remember, SOHCAHTOA can help us to do that easily. So we know that the sine of theta will be equal to opposite over hypotenuse. So the opposite side here is 8. The hypotenuse is 17. So the sine is 8 over 17. And we always want to check to see if we can reduce this. Unfortunately, we can't do that this time. Cos theta is adjacent over hypotenuse from SOHCAHTOA, adjacent over hypotenuse. So that would be 15 over 17. Also irreducible. Tan theta is simply opposite over adjacent. It's 8 over 15. Also irreducible. And we can get the three others by simply flip-flopping the fractions. So 17 over 8, 17 over 15, and our cotangent is 15 over 8. Pretty simple. Okay. Let's try another example. What happens if we're not given the triangle? So if theta is an acute angle and sine of theta is 2 over 7, find the other trig functions. For the angle theta. Alright, so for this example, we are not given the triangle, but we are given the fact that theta is an acute angle and that the sine of this angle is 2 over 7. So we can build our own triangle. So here, let's draw it. Let's say theta is right here. Here's our right angle. So it is known that the sine of theta is 2 over 7. So remember, the sine is opposite over hypotenuse. So the opposite side will be 2. The hypotenuse is 7. So opposite side is across from the angle. That would be 2. And the hypotenuse, our big side, is 7. So we know that the sine of theta is equal to 2 over 7. Let's go ahead and set up our landing pad for the other ones. We'll just fill in the fractions as we go. So before we do that, we need to know that last side. We can find that by using the Pythagorean Theorem. So Pythagorean Theorem, c squared equals a squared plus b squared. We call c must be the length of the hypotenuse. So that has to be 7. And a or b could be 2. So let's just say that this is a. Okay? So 7 squared equals a squared plus 2 squared. Right, so this one's not as simple as just plugging into the calculator like last time. We have to do a little bit of solving here. So 7 squared is 49 equals a squared plus 4. Okay. Subtracting 4 from both sides, we'll get 45 equals a squared. And square root both sides to cancel the square. So a is equal to the square root of 45. Now, the square root of 45 can be simplified a little bit more, okay? So we know that this 45, basically when we want to simplify a square root, what we can do is break this up into its factors, and one of the factors, we're going to try to get it as a perfect square. So is there a perfect square that divides evenly into 45? What's the largest perfect square that divides evenly into 45? Well, if we kind of go through our list of perfect squares are 1, 4, 9, 16, and so forth. Do you see a perfect square that divides into 45 evenly? And that would be equal to 9, right? So square root of 9 times 5. Alright, 9 times 5 is equal to 45. So 9 is the biggest perfect square that divides 45. So what we can do, since this is a product, we can take the square root of each of them and multiply. The square root of 9 is 3, and the square root of 5 is the square root of 5. So 45, square root of 45 is equivalent to 3 times the square root of 5. We'll just check that real quick in the calculator. So what is the square root of 45? 6.7-ish. And 3 square root 5, also 6.7-ish. So our A is 3 root 5. Alright, so let's go ahead and get our cosine. Cosine of theta is adjacent over hypotenuse, 3 root 5 over 7. And we check to see if this is reducible. Can we divide any number out of 3 and 7? No, so that's as far as we can go there. Tangent is opposite over adjacent, so that's 2 over 3 root 5. And of course we would want to rationalize this, so let's multiply by the square root of 5 over the square root of 5. So tangent becomes 2 root 5 on top over, now this would be 3 times root 5 times root 5. Well, root 5 times root 5 is 5, and 3 times 5 is 15. Cosecant is just the flip of this, so that's 7 over 2. Secant is the flip of this, so that would be 7 over 3 root 5. Of course, we would want to rationalize that, so let's multiply here by root 5 over root 5. So we get 7 root 5 over 3 times root 5 is, again, 15, like last time. So our secant is 7 root 5 over 15. And lastly, the cotangent is just the flip of our tangent, so 3 root 5 over 2. All right, let's do one more of those. Solve the right triangle. Having hypotenuse of length 4 square root 3 and one angle of 60 degrees. Okay. So let's draw our right triangle. Here's our right triangle. Okay. We know that one of the angles is 60 degrees, so I'm going to put that one right here because it's the bigger of the two. 60 degrees. And we know the length of the hypotenuse is 4 square root 3. Okay. So now, when I say solve the right triangle, what this means, solve the right triangle means find all sides and angles. Okay, so keep that in mind. So what we want to do is figure out all of these both of these sides and this angle right here. Okay. So here's how we can do that. So I'm going to label the, I'm going to go around and label the vertices of this triangle as A, B, C. I'm going to label all of the sides as lowercase letters corresponding to the opposite angle. So here, if this, let's say this angle is A, and this angle is B, and our right angle is C, then this side will be little a, and this side will be little b, and the hypotenuse is little c. That way it corresponds to the Pythagorean Theorem. Okay? So our mission is to figure out what angle A is, what is this angle, and what are the two side lengths, little a and little b. Okay? So the angle A is easily found here, right? Because we know there's a relationship between the three angles inside of the triangle, and that is that the angle A plus angle B plus angle C must be equal to 180 degrees, right? So angle A is equal to 180, take away the sum of these two angles. So 180 degrees minus 60 degrees plus 90 degrees. Well, what is that? Well, 60 plus 90 is 150. 180 minus 150 is 30. 30 degrees is angle A. Okay. Now we need to figure out what the sides are, right? Now we can't use the Pythagorean theorem quite yet because we have two unknowns. So c squared equals a squared plus b squared is not the way to go here. So let's figure out, let's say, side A. Okay, so if we're going for side A, note that we have angle A and we have the hypotenuse, right? So if we want to figure out what angle A is, we can use one of the trigonometric ratios to get that. So what, if we're dealing with this angle 30 right here, what trig ratio relates A with the hypotenuse? Well, note that A is the opposite side, so we're looking for the opposite side and we have the hypotenuse. So let's try using the sine of the angle 30 to get that value, right? So to find angle A, we set up an equation. Sine of 30 degrees equals A over 4 root 3. Okay. Well, what is the sine of 30 degrees? So let's make sure that our calculator is in the proper mode. You want to make sure that your calculator is in degree mode if you're working with degrees. So if you have a graphing calculator, if you hit mode, go down and go over and highlight degree and push enter, that'll get it for you. If you're using another calculator, just make sure that you have it in degree mode. So sine of 30 degrees is 0.5 or 1/2, right? We could have gotten that from the unit circle, right? We know that the sine of 30 degrees is 1/2 from the unit circle. So 1/2 equals A over 4 root 3. To solve this, we can just cross multiply. So I'm going to cross multiply. Therefore, 2A, 2 times A, must be equal to 1 times 4 root 3, or 4 root 3. Dividing by 2 gives A equal to 4 root 3 over 2. And we can do a little cancellation there. So A is 2 square root 3. 2 square root 3. To find B, we can do that process again, maybe use a different trig function, or since we know two sides of the triangle, we can simply use the Pythagorean theorem to get it, right? So to find B, let's do c squared equals a squared plus b squared. We know two of the values now, so 4 square root of 3 all squared equals 2 square root of 3 all squared plus b squared. So what is 4 square roots of 3 squared? 48. What is 2 square root of 3 squared? When you're doing this in the calculator, make sure that you have those parentheses there. Otherwise, it's not going to square everything. Just this is 12 plus b squared. And let's subtract our 12. So 36 equals b squared. Taking our square root, b is 6. So there we go. We've solved the triangle, right? We found all the sides and all the angles. So we're good to go with that one. Okay. So that does it for 10. So this is kind of just setting you up to find some angles and sides. But the big push for this is actually doing some applications with these right triangles. Okay, so again, we're going to deal with some applications. Before we get started, we just want to do a definition, a couple definitions. The angle between an observer an observer's line of sight and the horizontal have let's say the angles between an observer's line of sight and the horizontal have special names. If the line of sight is above the horizontal, we call this angle, the angle of elevation or inclination. If the angle is below the horizontal, we call this the angle of depression. So what do I mean? So if we have some person here, let's say their line of sight is going upward like this, and here we're having the horizontal there. This is the angle of elevation. This angle here is called the angle of elevation. If, let's say they're looking down at the ground, here's the horizontal, this angle is called the angle of depression. So you may see this terminology in your example problems, okay? All right, so let's take a look at our first example over to the right there. Number 1 says a kite is caught in the top branches of a tree. If the 90-foot kite string makes an angle of 22 degrees with the ground, estimate the height of the tree by finding the distance from the kite to the ground. Okay. Example 1. All right, so basically all we need to do is figure out what that height is. We know that we're dealing with a right triangle, so what I would always do is just draw the right triangle without all the bells and whistles, without any kites or trees or anything like that. And we'll input our info back. So 22 degrees. We have 90 feet here, and we're trying to figure out h. Okay. So what we need to do is, since this is a right triangle, we can use the trigonometric ratios to help us out, right? So always identify the sides that you're working with. We have our opposite side, which is h, and our hypotenuse here, which is 90, right? The angle is 22 degrees, so this would represent the opposite side. If the angle were right here, actually this would be the opposite side. So the opposite and adjacent switch depending on where this angle lives in the triangle, okay? So let's think about it. So Gatoa tells us that the sine ratio relates the opposite to the hypotenuse, right? Opposite and hypotenuse are what we're working with. So we're going to choose the sine ratio to help us out to find h, okay? So the sine of 22 degrees must be equal to opposite over hypotenuse, h over 90, okay? So let's figure out how to solve this thing, okay? So let's look at the sine of 22 degrees in our calculator. Sine of 22 is equal to 0.346. So let's replace the sine of 22 with what it's equal to. 0.3746 equals h over 90. Now to solve for h, all we need to do is just multiply by 90 on both sides. They'll cancel over here. So h will be equal to, just multiply the previous answer by 90. Looks like 33, so approximately 33.7. And we need some units here because we're dealing with an application, so that would be feet. We're dealing with feet here. Okay? So that's it. We've just found the height of that tree, which is nice, right? Because right triangles exist a lot in real life. They're everywhere if you look. So we can actually use these techniques, these math techniques, to find the heights and distances of certain things, okay? Let's look at our second example. All right, so it says a surveyor uses an instrument called a theodolite to measure the angle of elevation between ground level and the top of a mountain. At one point, the angle of elevation is measured to be 41 degrees. A half kilometer farther from the base of the mountain, the angle of elevation is measured to be 37 degrees. How high is the mountain? So you can see here that we have our diagram set up. We have some, so here you can see that first angle that he measured was 41 degrees, and then half a kilometer farther, it was a little lower, 37 degrees, okay? We're trying to figure out what the height of this mountain is. We only know this distance between the two measurements, so it looks like they're calling this measurement z, okay? So this one's a little tougher than last time because we're dealing with two right triangles. You can see the one right triangle dealing with the 41 degree angle, and the other right triangle has the 37 degree angle. So we're going to have to do a little bit more work here to figure that out. So again, what you want to do is get rid of all the bells and whistles from the diagram that they give you. So here, let's say, 37, 41, here's Z, here's H, here's 0.5. Okay. All right, so let's see how we're going to do this one. Well, notice that we don't have any sides of any of the right triangles, right? We don't have any sides, so it's going to be a little tougher than the last problem because we knew a side. So we're going to have to do a little bit of extra stuff here. So what do we know? What do we know? So I know that this entire distance for the larger of the two right triangles, that big right triangle there, is the sum of these two guys here. So this would be z plus 0.5, right? Z plus 0.5 here. So I can represent h in two separate ways. One using the big overall triangle, and the other one using this smaller inside triangle there. Okay? So let's see what I can do. So let's just kind of focus in on the red triangle, the big triangle here. So we know the angle is 37. We know the opposite side from 37. So again, we're kind of disregarding the other triangle there. The opposite side here for 37 would be h. And the adjacent side down here is z plus 0.5. So what trig function helps us out with opposite and adjacent? So Patilla says the tangent tells us about the relationship between the opposite and adjacent. So for our big red triangle here, we know that the tangent of the angle in the red triangle is 37. Must be equal to opposite over adjacent. Okay. So let's see if we solve this for h. What is the tangent of 37 degrees? Tan of 37 is 0.7536. 0.7536. So we round to 4 decimal places equals h over z plus 0.5. Now we can solve this for h by simply multiplying by z plus 0.5 on both sides. Okay. So we'll have here 0.7536 times z plus 0.5 equals h. Okay. Now, so we have h solved for here, but we need to figure out its value. So we've got to try and find z or have some other equality for h so we can get an equation here. So for the smaller blue triangle, note that we know the angle is 41. The opposite side is h, and the height of the mountain, and the adjacent side is z. So again, we have opposite and adjacent, so tangent can help us out. So we know that the tangent of 41 degrees is equal to h over z. Solving for h, we just multiply by z on both sides. Well, before we do that, let's find the tangent of 41. The tangent of 41 degrees is 0.8693, which is equal to h over z. So now if we multiply by z on both sides, we get 0.8693z equals h. Okay. So notice that we have two expressions involving h, right? And the h's are the same in both cases. So what we can do is set these two sides equal to one another, these two sides of the equation. So 0.7536z plus 0.5 equals h, and so does 0.8693z. That also equals h. So that means that these two expressions must be also equal to each other. So this implies that 0.7536 times z plus 0.5 must equal 0.8693z. So now you can see that we have an equation that involves z only, so we can solve this. So we're just going to distribute like normal, just with these weird values. So let's see what we get. If we distribute here, we'll get 0.7536z plus, all right, let's multiply that, 0.7536 times 0.5 equals 0.3768, which equals 0.8693z. All right, now we can isolate z, so we'll subtract 0.7536z from both sides. Just cancel here. 0.3768 equals 0.1157z. And then divide by 0.1157. Cancel here. So z will equal 3.26 kilometers. Okay. Now, is that all we need? Are we looking for z? Well, let's go back to the problem. The problem asked us to find how high is the mountain, right? So we're looking for h, not z, right? So we need to figure out what h is now, and that's pretty simple because we have two expressions involving h and z here, right? So we know that h is equal to 0.8693 times whatever z is, or h is equal to 0.7536 times z plus 0.5. Either of these can find h for us. So we're going to have to substitute this 3.26 into one of these z's. Either or, it doesn't matter. Looks like this one's going to be the easiest for us. Therefore, h is equal to 0.8693 times 3.26. So let's see what that is. Looks like 2.83 kilometers. Okay. So this one was a little bit tougher than the last one because we had to equate two of the heights together. Okay, so sometimes we'll need to do that. All right, moving on. All right, number 3 says the top of a ladder, a 20-foot ladder, is leaning against the edge of the roof of a house. If the angle of inclination of the ladder from the horizontal is 51 degrees, what is the approximate height of the house, and how far is the bottom of the ladder from the base of the house? Okay, so we know we have this scenario involving this ladder. So we need to get a visual on it. So here we're not given the diagram, so we need to draw one ourselves, right? So kind of envision a ladder leaning up against the house. So let's say here's our house. Nice house, right? And a ladder is leaning up against the edge of the roof. So we have the ladder leaning against the edge of the roof. It's on the ground here, right? So what we're trying to do is figure out this distance here. So we have this right triangle being made by the ladder, the horizontal, and the height of the house. So let's fill in what we know. We know the ladder is 20 foot long. We're trying to figure out what the height of this house is. And we know that the angle of inclination of the ladder from the horizontal is 51 degrees. So recall the angle of elevation, or the angle of inclination, is the angle from the horizontal upward. So it's this angle right here is our angle of inclination, which is 51 degrees. Okay. So if we draw our triangle without all the bells and whistles, we have this right triangle, we have our angle of 51 degrees, h is here, 20 is there. We are also looking for how far is the bottom of the ladder away from the base of the house. So we're looking for this distance also. Let's call it z. Okay, so we're looking for z here as well. Two things that we're looking for. All right, so we can do this in either of two ways, right? We can find h first, or we can find z first, because we know one of the sides and one of the angles of the triangle. So let's go for z first this time, okay? So let's go for z. We can do this if we think about our SOHCAHTOA, right? SOHCAHTOA. We can find either h or z first, it doesn't matter. But let's go for z. So z represents the adjacent side, and we know the hypotenuse here, right? So we know, looking for the adjacent, we have the hypotenuse. Looks like the cosine function helps us out with that, right? So to find z, we'll use the cosine here. So the cosine of that angle, 51 degrees, must be equal to adjacent over hypotenuse, z over 20. So what is the cosine of 51? Cosine of 51 degrees is 0.6293. And then multiply by 20 on both sides. So cancel, so z will equal 12.59. And we're dealing with feet. This is 12.59. Alright, now we have to find h. So now that we know that these two sides, we can simply use the Pythagorean Theorem to find h, right? So we know that c squared equals a squared plus b squared. C is the length of the hypotenuse, so that's 20. Let's say our adjacent side is a, so 12.59 squared plus h squared. H is our b. Okay? So 20 squared is 400 equals, this value squared is 158.42 approximately, plus h squared. So subtracting, cancel, h squared equals 241.58, and then take a square root. So h is 15.54 feet. So we have the height of the house is 15.54, and the ladder is 12.59 feet away. All right, our last example. Is here. All right, so it says a drawbridge measures 7.5 meters from shore to shore. And when completely open, it makes an angle of 43 degrees with the horizontal. When the bridge is closed, the angle of depression from the shore to a point on the surface of the water below the opposite end is 27 degrees. When the bridge is fully open, what is the distance between the highest point of the bridge and the water below? Okay, so you can see here we have a couple of diagrams. Here we're looking for the distance from water to the very high point when the bridge is open. And we have two kind of triangles going on here. So let's think about what's going on. If we draw this, so when the bridge is open, we have this right triangle here. So we know that this is 43 degrees and 7.5 meters. And when the bridge is closed, we have 7.5 meters here. 27 degrees is an angle of depression there. So what do we need? Well, if we notice, the distance that we're looking for here is simply the sum. So let's say here's height 1 and height 2. Notice here, if we add this height from the horizontal to the top of the open bridge and this distance from the water to the closed bridge here, this distance and this distance, then we get the entire distance, right? So what we need to do is figure out what this guy is, h1, and what this guy is, h2, and d will be equal to h1 plus h2, okay? So we need to do that for each of those. So let's look. With this one, to find h1, we have the opposite and hypotenuse, right? So remember SOHCAHTOA. SOHCAHTOA tells us that sine relates opposite with hypotenuse. So for this guy, the sine of 43 degrees must be equal to h1 over 7.5. So of course here we can just multiply both sides by 7.5 and then we have h1. So h1 equals this product here. So we can do that all in the calculator at one time. So let's do 7.5 times the sine of 43. So again, 7.5 times the sine of 43 is 5.11 meters. Now let's look at this one. So this one we have 27 degrees here, so h2 is the opposite side, but is 7.5 the hypotenuse still? Well, no, because the hypotenuse is down here now, right? So this is the opposite, and this is the adjacent. So if we look at SOHCAHTOA, opposite and adjacent occur with the tangent function. So the tangent of 27 degrees equals h2 over 7.5. So again, here we can just multiply by 7.5 on both sides. So h2 equals 7.5 times tan. So we just do that in our calculator. 7.5 times tangent of 27. That's 3.82 meters. So D is 5.11 plus 3.82 or 8.93 meters. All right, so that does it for this lecture. You can go ahead and try the assignment problems for section 410 and 411.